You see a walkthrough to problem 2, design of a deep well pumping system for dewatering during construction. So an excavation contractor has to lower a groundwater table and would like to get the first idea about configuring a deep well pump as displays in the figure below. So this is how they want to excavate and get the water table. Based on the hydraulic situation, she expects the average inflow capacity is 1200 gallon per minute with a drawdown of approximately 20 feet, while the static head will be about 80 feet, and the horizontal distance to the discharge into the nearby canals is 330 feet. So as you can see that is 330 feet horizontal to the nearby canal, and the static head as shown in here. And then she has found that in this kind of situation, a vertical turbine pump is the most reliable and economical. Two types of pipes are available: 6-inch smooth steel or 8-inch smooth steel. And we have other assumption. And as you can see, this is more with the semi-open ended question. So that normally the real life that you have to face in the this type of problem. No one form a specific every detail problem. Sometimes we have to form the problem and solve. In this case, the problem give you some information. And the background and assumption, the total head equal to static head loss of due to friction inside the pipe and velocity head. So that go back to your hydraulics, hydrology, and fluid mechanics, and especially in the lesson that we deal with the water supply system, air compressor, and water supply system. In the previous portion of this class, we talk about that as well. So that way to review that lesson. And static head equal to the suction head from the water surface to impeller, and discharge head from the impeller to discharge. So that, as you can see, static head that define from here, and then this step. Okay, and then equivalent length of the regular 45 degree elbow is 20 feet for 8 eye pinch and 7.1 feet for 6-inch pipe. And this one they given, remember we have in the exam 1 reference, we can be able to determine the equivalent length for different fittings, if you recall that. And then the intake is 20 feet, the intake 20 feet. Friction losses as the function of pipe material, diameter, and flow capacity shown in the figure below. So in the water supply system class that we learned in the first portion of this class, we use the table. In this case, they give you the chart to determine the friction loss. And we are chart finding the efficient configuration, including the power requirement of the pump, which particular turbine pump model VIT from the year's pump match the capacity requirement. A finger in the last page show the hydraulic coverage of the VIT model. So this basically to determine the friction loss that the mentioned above. And this is a different pump provided by this company with the capacity versus the head at different areas. So basically, as you can see, semi-open, we need to determine the pipe, what pipe we use, because the available pipe is 6 inches and 8 inches. And then what is the total head needed, and what is the pump should be selected. So those are the questions that we need to do for this one. So with that, I walk through to you the solution. So from the chart that you saw here, and the average flow that this expect is 12 gallon per minute, 1200 gallon per minute. And as you can see from here, and we have a 12-inch steel pipe, and that one is steel pipe, and you can see copper and cast iron. So you have that one. And in the 8th cast iron, a steel pipe is the one that is PVC pipe, and then we have steel, and we have cast iron. So this is cast iron 8 inches, This one is PVC and this is steel. And for 6 inches, you have the same in there. For PVC steel, it will be the circle, so that in the middle there. So as you can see here, for the 1200 gallon, we have to choose, better to choose 8 inches because 6 is a little bit small for 1200 gallon per minute capacity flow. So as you can see, for steel, with 8 inches diameter should be selected. So that's why in the solution I say here from the friction loss chart, both available pipe size could deliver 1200, but as you can see, the 6 inches is a little bit small, so we select 8-inch pipe as I show you. And based on the definition of static head, static head is equal to the assumption that you see here, the assumption, suction head and discharge head, and it 55 plus 25 feet. So we can have that in here, 55, 25, 80 feet. And the length of pipe, they have the square root, because that one from the drawing, and you can see there, from the drawing you see in here. So you have that is 330 feet and this is 25 feet. So that one assume that is a diagonal of the right angles, hypotenuse of the right angles, right triangles. So you can use that equation to determine the length of pipe and plus the intake. Problem given 20 feet, so you will get 351 feet of pipe. And from that we have two elbows, 45-degree elbows, and you can see there, one here and one there, so 2, and each for 8 inches is the 12, so you will have 24 feet pipe, equivalent length for the two elbows. Total equivalent length, so from that we can have the actual geometrical length of the pipe, 351, equivalent length of the 15 is in two elbows, 24, so you get 375 feet pipe. And from that we can go to the chart. Go to the chart here to determine the head loss. Back here, go down to determine the head loss, and you can see there from the 1200 gallon per minute, be able to find out the head loss in there. And that head loss, and you can read in that equation, it's about 2.3, and you can see here, this is 1.6, this is 3.2, so that from here to there about 2.3, and that here the loss per 100 feet of the pipe length, and that's why we have to divide 100, and then we with 8.6 feet of water, so the head. So from that we can get the total dynamic head based on the definition. It will be equal to the head loss plus the so that the head loss here, and we get the static head 886 feet of water that is required for the total dynamic head. And then with that equation, you can see this equation from the final exam reference, very first page. You will see that QH over 3960 to determine from the foot of water to the horsepower, just basically the unit conversion in there with the gallon per minute. So we did here, Q is the flow, and flow here is 1200 gallon per minute with the water, 8.6 feet of water divided by 3960, we get 26.8 horsepower. And of course, like I said, this is semi-open problems. We need to consider the how efficiency the pump, how efficiency the engine, the motor that put power the energy for the pump. So that something we need to consider. So in this case, I assume efficiency for the pump is 80%. Then just try to make it realistic, right? The pump horsepower, it divide by that, so it had to be more, so it will be 33.6 horsepower. And then of course the motor will provide energy for the pump if they have its own inefficiency. So that I assume efficiency factor in this case 90%. You can assume 80% because that depends on the situation of the pump, the situation of the motor. You will, as the engineer, you will decide what that. And with that here, the engine for the horsepower divided by 0.9, we have 37.5 horsepower. And from that, I select the VT1 pump model 1760. So you have that here. With different model you select, of course, other model can be fit, but we select this model. Why that? If you go to the finger here, so you have that the vertical line, as you can see, the vertical line is 1200 gallon per minute capacity requirement, and with the you see the 1760 drop per minute, and it intersect at this one, and it will get the head feet is about the one we want at least 88.6 feet total head total head, and that will in the area of high efficiency of the pump work. So that's why it's good to have. You may select other the pump that other models that have it. This one apparently as you can see give you one example that is not working for this pump. For example, this pump is 3500 rad per minute, so you have 1000, so it will be here, and ours is 80 or something here. So it's about to get into the efficiency zone, but it may not be a good idea for that. But if you go to the one that we select 1200 here, go to efficient zone, and similar for other models it can be matched well. For example, this one A80, we can have 12, go to A80 it in selecting zone, so that we can select a different pump that meet the need of our problems, not only